The first proof is a bit sketchy and therefore is quite easy to solve. We're all familiar with infinite series, and this one is no different. It has a ratio, r, of 2 and a first term of 1, so it looks like this. No one can argue that this will add up to a very large number, and with an infinite number of terms it will add up to infinity. Now all I'm going to do is multiply this series by 1, which will leave us with the same answer. Again, this is standard and you can't really see any mistakes yet. Now 1 is just 2 minus 1, so we can multiply the series by 2 minus 1 and we should end up with the same answer, shouldn't we? But no, have a look. We end up with 2 plus 4 plus 8 plus 16, etc. because we're multiplying it by 2. But over here we also have minus 1, minus 2, minus 4, etc. So everything here apart from minus 1 cancels out everything up here. So therefore this all equals minus 1. That is to say that infinity equals minus 1 if you imagine we carried it on. So there we go, infinity equals minus 1. Finished. Done. QED. How on earth can this be true? As you may have figured out, this proof is about as real as saying that pi equals 4. Obviously the problem with that is not everything that is multiplied by 2 is cancelled out. In fact, it is everything but the last term in the series, which will be the largest, and so with an infinite number of terms, cancelling out all but the last term of the series, it means the total will be minus 1 plus whatever the last term is, which incidentally will be pretty big as r equals 2. So therefore adding up this series does not equal minus 1, sadly, and it really is like saying pi equals 4. Talking of which, this is the proof that pi is equal to 4. First we start with a circle of diameter 1, so that the circumference is pi. Then we draw a square around the circle where each side of the square is a tangent to the circle at that point. As you can see, this square has a perimeter of 4 and a width and length of 1. Now let's do something here. Let's bend the corners so that they touch with the circle. The perimeter is still 4, we've just got a dodecagon. Let's repeat this process again, bending in the corners so that the perimeter of what was the square, but is now an icosaicoctagon, is still 4. Do you see what is happening? I mean, apart from the square gaining more size and consequently becoming harder to pronounce, it is becoming more like the circle it surrounds, with every step of the corners folding in. I know my drawings aren't great, but is it possible that with an infinite number of fold-ins the square will become a circle? I mean, it's getting closer to the circle all the time, as more parts of it are touching it. As we haven't actually cut off any bit of the shape, the perimeter of it will still be 4. What do you guys think? On the face of it, I think this proof seems pretty credible. However, it's obviously not true. The first reason being pi is not 4. It is universally recognized as 3.14159265359, etc. And to say it equals 4 is like saying the earth is flat and that the square root of 2 is 2, even though the latter can be quote-unquote proved using the same method we did for pi with triangles. But I digress. The second and perhaps more involved reason that pi does not equal 4 is that we're not actually folding in the square to make a circle. Even with an infinite number of fold-ins, a close look would reveal a crinkled surface. It would be a very close look, and it would be very close to a circle, yes, but actually it would be a polygon with thousands of sides. Imagine if this was real, then it would be like a crinkled ball, with the crinkles very, very small along the surface. If we then inflated the ball, the little crinkles would smooth out, and in a two-dimensional view we would see that we have a circle with circumference 4. The only problem being that when we inflated it, we increased its diameter, so that the diameter is more like 1.27 and not the round number 1 we started with. Thus the ratio of pi still holds, and we can breathe a sigh of relief knowing maths has not exploded. In fact, this method is similar to what was used by Archimedes to approximate pi, and he ended up proving pi was somewhere between 223/71 and 22/7. And that's pretty calculated considering it was around 2,300 years ago. And that's about all I have to show you today. Thank you for listening.